Greetings and welcome to Distiller. In the previous class, we discussed about entropy. So, entropy is physically defined as the degree of randomness. Okay, so for a process to take place spontaneously means that the process will take place on its own without some external force, external driving force applied. Okay, the process will take place naturally. In that case, the process is spontaneous. For example, melting of ice. All right, if you keep ice at room temperature, then it would automatically melt. All right, so that is spontaneous process. So for a spontaneous process, the change in entropy is always positive. All right. Then we discussed that entropy is defined as the heat transferred, sorry, not dt, t, dq by t, right? So heat transferred per unit temperature, that is known as entropy. ds is equal to dqr by t. All right, this is one important definition of entropy. And in order to evaluate entropy change between temperatures T1 and T2, we have to integrate this entire thing. All right. So then we use the first law of thermodynamics saying that dqr is equal to du plus dw, and du can be written as cv dt and dw can be written as pdv, right? So when we use this equation, so we get ds is equal to cv dt by t plus p by t dv, that is r dv by v. So now when we find delta S, we get this as cv ln t2 by t1 plus r ln v2 by v1, right? This is the first equation of entropy, first very important equation that we got. And after that, the second equation for entropy that we got was by keeping cv is equal to cp minus r. So when we do that, we get delta S is equal to Cp ln T2 by T1 minus R ln P2 by P1. Okay. This is the second equation. So these two equations are very important for entropy, for entropy calculations. All right. And then we discussed entropy calculations for different types of processes in which there are two processes which are very important. First is adiabatic process. So for adiabatic process, since we have dqr equals to 0, so we even get ds or delta s as 0. All right. So an adiabatic, a reversible adiabatic process can also be considered as an isentropic process. All right. And the second was isothermal mixing. So in isothermal mixing, we get entropy change is equal to minus R sigma yi ln yi. All right. So this is what we discussed in the previous video. Today, we are going to solve certain problems on entropy. All right. So without wasting more time, let's move on to the first problem. An ideal gas at 2 atm and 500 Kelvin undergoes the following changes: isothermal compression to 5 atm, isobaric heating, adiabatic expansion to initial state, and if gamma is equal to 1.4, calculate all these things. All right. So this is a very simple process, a very simple problem, but yes, it involves quite a lot of steps. So for such a problem, we already discussed in the previous few videos, the first step is always to draw a PV diagram. All right. We need our PV diagram for this process, right? So this is our pressure, volume. Okay. So let's draw the PV diagram for the same. So its initial state is 2 atm and 500 Kelvin. So let's mark it somewhere here. Pressure is going to be 2 atm and temperature is 500 Kelvin. 500 Kelvin. All right. Then, since it is undergoing isothermal compression, so the shape of the curve is going to be something. Just a minute. The shape of the curve for isothermal process, an isotherm, it is something like this. So it's going to be like this. Let's say this is the next state. So since it is isothermal compression, therefore the pressure here, we already know it's 5 atm, and the temperature is going to be same as A. So it's going to be 500 Kelvin. All right. Then we move on to the next, that is isobaric heating. So for isobaric heating, since the pressure is constant, right? The pressure is constant and heat is being added. So that means there would be an increase in temperature. And at constant pressure, if we increase the temperature, then in that case, there is an increase in volume. So it would go in this direction, right? So here you will get C. This is point C. Okay. So it is heated isobarically. So therefore the pressure is 5 atm. We don't have enough idea about temperature. So we'll not write anything over here. Okay. And then finally it goes adiabatically to its initial state. So it's right. This is my PV diagram. Okay. Now A to C is an adiabatic process. Let's first complete the PV diagram before we go ahead. So A to C is an adiabatic process. So therefore, we have PA VA to the power gamma is equal to PC VC to the power gamma, right? Or we can also say PA to the power 1 minus gamma, TA to the power gamma is equal to PC to the power 1 minus gamma, TC to the power gamma, right? So we have TA, we need to find TC. So TC is going to be TA into PC by PA to the power gamma minus 1 by gamma. All right, PC is 5, PA is 2, gamma is 1.4. So putting all these values, we get TC is equal to 649.63 Kelvin. All right, 649.63 Kelvin. So we'll put it over here, 649.63 Kelvin. Now our PV diagram is complete. So once our PV diagram is complete, then we move on to the further steps. All right. So now we have to go for each step. So first of all, we'll go to step 1, that is A to B, isothermal compression. So since we are going from A to B, for an isothermal process, delta U is equal to 0. And for an if we talk about heat, so heat dq is equal to dw, so heat would be equal to work done, right? And work done in an isothermal process is equal to RT ln P1 by P2. So that means PA by PB, right? So that is RT ln 2 by 5. So we get work done is equal to minus 3809 joule per mole. All right, minus 3809 joule per mole. So heat added would be equal to minus 3809 joule per mole. Now, by sign convention, we obviously know that this negative work done implies that work input, there has been work input, while the negative heat transfer implies that there has been heat output. So work has been added in and heat has been taken out. All right. So this is the sign convention that is followed. Okay. And finally, we also need in this, apart from work, heat, internal energy, we also need entropy. So we are going to calculate entropy. So this is an isothermal process, right? So for an isothermal process, the entropy change is given by R ln V2 by V1 or P1 by P2. So we are going to take R ln P1 by P2. That is R ln 2 by 5. So entropy change is minus 7.618 joule per mole Kelvin. All right, joule per mole Kelvin. So that is the entropy change. So this is what we have got from the first step. Okay, then we move on to the next step. That is step 2, which is B2C isobaric heating. So in B2C, your internal energy is going to be CV delta T. Now, delta T is TC minus TB, that is 649.63 minus TB, which is 500. So that is CV into 149.63. Okay. Now, how to calculate CV? We know gamma, right? We know gamma. So since we know gamma, we know that Cp by Cv is equal to gamma, implies Cp minus Cv by Cv is equal to gamma minus 1, correct? And Cp minus Cv is nothing but R. So we have R by Cv is equal to gamma minus 1. Hence we get Cv is equal to R upon gamma minus 1. And at the same time, we get Cp is equal to gamma Cv, that is gamma R upon gamma minus 1. All right. So for this particular problem, we have Cv is equal to 20.785 joule per mole Kelvin. And we have Cp, this is Cv, right? And we have Cp is equal to 29.099 joule per mole Kelvin. Okay, so we'll put this value over here and we'll get CV. Sorry, we'll get internal energy change is equal to 3110.06 joule per mole. All right, this is delta U. Then for an isobaric process, we have W is equal to P delta V, which can be written as R delta T, right? So this can be calculated as 1244.024 joule per mole. All right, this is how we get the work done. And the heat transferred is equal to, for a constant pressure process, it is Cp delta T. So that is going to be 29.099 into 149. So heat transferred we get as 4354.084, right? Joule per mole. Okay. And if you see, this is actually in accordance with the first law of thermodynamics. Q is equal to delta U plus W, right? And then we have to find the entropy change. So entropy change for an isobaric process is going to be Cp ln T2 by T1. That is Cp we know. T2 is 649.63 and T1 is 500. So we'll put the values over here. And delta S, we get 7.618 joule per mole Kelvin. All right, that's what we have. Now we move to the next step, that is adiabatic expansion. So adiabatic expansion is from C to A. So for an adiabatic process, we have delta S and Q as 0, right? Delta U is same CV delta T. So this time T, the final temperature, that is TA is 500 and TC is 649.63. All right, so we'll get minus 149.63 CV, which is equal to minus 3110.06. joule per mole. Okay. And we also know that by first law of thermodynamics, dq is equal to du plus dw. Hence, work done is negative of internal energy change over here. So that is equal to 3110.06 joule per mole. Or else we can also use the formula for work done of an adiabatic process. But this seems easier in this case, so we are going to use this. All right. So once we've got all these things, so we'll finally add them up. All right. So for the net cycle, we'll have net work done is equal to the summation of all work done, right? So work done AB in BC and in CA. So in AB it is minus 3809 joule per mole. In BC it is 1244.024, and over here it's 3110.06. So finally the work done comes as 545.08 joule per mole. Okay, 545.08 joule per mole. That is work done. Okay, then we find heat. So for a cyclic process, we should know that internal energy is always zero, because internal energy is an intensive. Internal energy is a state property. All right. So therefore, for a cycle, it's going to be zero. All right. So finally, from first law, you'll get Q is equal to W for a cycle. Therefore, it's going to be 545.08 joule per mole. To verify that you've not made any mistakes, you can actually add the heat in each case, in each step, and you'll get the same result. All right. And finally, you have to get the entropy change. So entropy change, you're going to add all of them. So if you're going to add entropy in first step, second step, and third step, it's zero. So it's minus 7.618 plus 7.618. That's zero, right? It is again zero. So keep this in mind. Entropy as well is a state property. All right. Entropy as well is a state property. Okay. So it does not depend on the path. It only depends on the state. Okay. It depends on the state of the system. Okay. We'll further study that entropy is actually a function of temperature and pressure. All right. So if there is a change in temperature and pressure of the system, then entropy of the system is going to change. Right. So temperature and pressure are both state variables. Hence, entropy itself is a state variable. All right. So therefore, for a cyclic process, entropy is going to be zero. Okay. So that's how we got this result. Okay. So now we move on to the next problem. A 40 kg steel casting at a temperature of 450 degrees Celsius is quenched in 150 kg of oil with this as its CP at 25 degrees Celsius. If there is no heat loss, what is the change in entropy of steel casting, oil, and both considered together? So you have to keep this in mind that entropy change delta S is basically integral of dq by T, correct? And dq under normal conditions where pressure change is taken negligible. So we consider most of the processes are as constant pressure process. So dq is taken as mcp dt, right? So when we integrate, we get entropy change as mcp ln T2 by T1. All right. mcp ln T2 by T1. This is what we get. So now for steel casting, you have M is equal to 40 kg, Cp is 0.5, and T1 is 450 degrees Celsius. T2 is not known, right? So for this, first of all, we have T1, which is equal to 450 degrees Celsius. That is the initial temperature, right? This is the initial temperature, right? Now, how to find the final temperature? So for that, we are going to do energy balance. All right. So energy balance in this case is heat lost by steel casting is equal to heat gained by oil, right? So heat lost is equal to heat gained. So MCP delta T for steel is going to be MCP delta T for oil, right? So M for oil, M for steel is 40, Cp is 0.5 kilojoule per kg Kelvin, and delta T is going to be 450, not 450, 773. Take this in Kelvin. So it's going to be 773, sorry, 720 minus, let's assume the temperature finally attained is T. We have taken 723 minus T because we basically take modulus of heat. So heat is going to be negative because the heat is lost. But since we are going to take the magnitude of heat transfer, therefore we have taken higher temperature minus lower temperature. Okay. And that is going to be the heat gained by oil. So that is 150 kg of oil. Specific heat is 2.5. And initial temperature is 25 degrees Celsius, which is 298. Final temperature is definitely going to be greater. So it's going to be like this, right? So when we solve for T, when we solve this particular equation, we get T is equal to 319.52 Kelvin. All right, 319.52 Kelvin. That is heat. All right. So finally, the final temperature that is gained is 319.52 Kelvin. Okay. So entropy change for steel casting is going to be M Cp ln 773 by 319.52. So delta S for oil would come as 26.1474. I'm so sorry. It's going to be for oil T2 by T2. So 319.52 upon 723. So 319.52, that is the final temperature, upon 773, that is the initial temperature. So that's going to be minus 16.332. The unit is going to be kilojoule per Kelvin, right? That is the entropy change for steel casting. All right. Then we move on to the next part where we have to take oil into consideration. So delta S oil is going to be MCP ln T2 by T1, right? So final temperature of the oil is 319.52. Mass of the oil is 150. Specific heat is 2.5. Ln 319.52 upon the initial temperature was 25 degrees Celsius, which is 298 Kelvin, right? So entropy change comes as 26.1474 kilojoule per Kelvin. Okay, kilojoule per Kelvin. So therefore, the net change in entropy, total change in entropy is going to be entropy change for steel plus entropy change for oil. All right. So that's going to be 9.815 kilojoule per Kelvin. All right. So when you have two systems, or you basically have two components in your system, steel and oil, you first of all conduct an energy balance to achieve the final temperature which the system has attained. All right. After this energy balance, when you get the final temperature, then you find the entropy change. All right. So entropy change for the entire system is going to be entropy change for each component added to each other. All right. So entropy change for steel and oil over here. So entropy change for steel is MCP into final temperature into ln of final temperature upon initial temperature, and same for oil. So that's how we get the total entropy change. All right. Now the total entropy change is positive. Hence, we get that the system, this change that took place is spontaneous in nature. All right. The change that took place is spontaneous in nature. That's what we get from here. Okay. Now we move on to problem number 3. A gas is heated in an isobaric process from 300 Kelvin to 1200 Kelvin. Find its entropy change if Cp is given to be this. This is the easiest possible question you can ever get. ds is equal to dq by t, which for an isobaric process can be written as Cp dt by t. Therefore, delta S is going to be integral of Cp dt by t. And over here, they have given Cp as a function of temperature. So it's going to be 27.3 ln T2 by T1 plus 4.2 into 10 to the power minus 3. T by T is going to be 1. Integral of 1 is T. So T2 minus T1. So T2 is 1200, T1 is 300. So you'll get the total entropy change as 41.62 kilojoule per kilomole Kelvin. All right. So that is your result. This is the easiest possible question from entropy that you can get. Now, this is an interesting kind of a question. So determine the saturation temperature of water using the following data. So the specific volume, internal energy, enthalpy, entropy, all these are given. All right. Now remember, over here, we are actually talking about phase change. All right. Over here, we are talking about phase change. So we know that entropy is equal to dq by t, right? And during phase change, the heat transferred is equal to the enthalpy of phase change, right? So in let's say the fusion is taking place. So enthalpy of fusion upon the freezing point, right? Similarly, let's say vaporization is taking place. So in that case, delta S for vaporization is going to be enthalpy of vaporization upon boiling point. Okay, so basically, in order to calculate entropy change for phase change, what we need to do is we need to find the enthalpy change during the phase change and the saturation temperature. All right. So using that, we can get the entropy change. Okay. So now over here, they have given us the enthalpy change and entropy change, right? They have given us enthalpy change and entropy change. We're only supposed to find the temperature. So that's very easy. So the change in entropy is equal to delta H by T. Hence, saturation temperature is delta H by delta S. So delta H is 2748.7 minus 640.23. 2748.7 minus 640.23 upon entropy change, which is 6.8213 minus 1.8607. 6.8213 minus 1.8607. Okay, so that's what we have to calculate. So the saturation temperature, it comes as 425.04 Kelvin. All right. And this can actually be verified from stream tables as well. And this problem can be done from stream tables as well. You can just go to the stream tables and find that at what temperature do you get these data values. So that can be possible, but solving it using entropy made it very easy. Instead of going and searching for a stream table, we can actually use this data and directly find the saturation temperature. All right. So this is how we get the results for entropy. So hope whatever problems we did, they were clear. All right. Make sure you practice a few more problems on entropy. We'll be doing a few more problems as well. And you can practice more problems from various books. Entropy is a very important topic, and it's a very interesting topic as well. All right. We'll be continuing further with entropy from the next video.